After seeing what the memory hierarchy is, now we're going to jump over into cache organization. So just a quick reminder about adding cache to a computer. What a cache is doing, it's exploiting data locality, temporal and spatial locality, to reduce the number of external memory accesses. And the idea is to copy commonly accessed data into an on-chip memory, which is an SRAM. So we have a CPU over here. We're usually, due to Harvard architecture, going to have an instruction cache and a data cache. That's going to be like the first level cache. Then we'll have a level 2 cache, a level 3 cache. They're going to be bigger and bigger. Finally, we're going to go to a DRAM controller and go out to DDR. Okay, so the idea is to copy it over to there. What we usually do is we call these things lower level caches and these higher level caches. The problem is it's really hard to know what that means, because what is higher, 1 or 3 and so forth. So the better kind of nomenclature is to call these ones inner level. The inner level, level 1 is an inner level cache and level 3 is an outer level cache. And that is a better way of telling it, because inner is closer to the CPU and outer is farther away. So I'm going to try to use that terminology, though I may get confused a little and say higher and lower, because it's a common kind of way to call it. Okay, again, L1 is divided into the instruction cache and the data cache, where the other levels are going to be shared at least between instruction and data usually, and sometimes shared between multiple cores. So let's look at a basic cache. A cache, we said, is a subset or a copy of an outer level of memory. And so when accessing data, we need to check if the data is in the cache, because if it's in memory, we have to go and get it from memory. And therefore, we have every byte of data needs to somehow be tagged with an ID. So in this case, we see that the DRAM, has all kinds of data in it, and it has IDs for each of those data. And when we bring it into the cache, we took this guy over here, which had ID number 1 and data number 1, and put it in the cache. So we store it as data number 1, and we have some sort of another array that has the IDs where it stores that as ID number 1. And so when we go and we're going to load word to register T0, where you want to load ID 3, what we're going to do then is go and find ID 3 and say, aha, we have a cache hit. The address we were looking for, the ID that we were looking for, is inside the cache, and therefore we can go and immediately bring data number 3 into our register. And the time it takes to actually go and check that we have that ID inside our cache and to bring it into our register and do whatever we want with it is called the hit time. The other cases where we're going to load word, to register T1, we want IDX. And if we look over here, we don't have IDX over here inside the cache. And so it was not found, and that is a miss. So that is a cache miss. And in the case of a cache miss, we have to go and decide on on where we're going to put that ID, and sometimes our cache is full, and then we have to evict somebody. So in this case, we decided to evict data number N from the cache and replace it with IDX. So we're going to go get rid of that and place data X and IDX inside the cache. And at the same time, we're probably going to already go and bring data X into the register. We can do other things like rerun the instruction or something else after we get a miss. But generally, if we're already bringing it in, we'll just complete the operation. The time elapsed that it takes us to go to that outer level of memory, for sure, if it's something like DRAM, is going to be much larger than our hit time, and so we call that a miss penalty. So then we have two important kind of figures of merit. One of them is the hit ratio, and hit ratio is the number of hits divided by the number of hits plus the number of misses, and miss ratio is the opposite, how many misses we have divided by the total number of accesses. So hit ratio is 1 minus miss ratio, and miss ratio is 1 minus hit ratio. And that brings us to our main goal, which is usually going to reduce the average memory access time, or the AMAT. And that's kind of the performance metric that we define for caches and we want to reduce. And AMAT is the hit time, the time it takes to actually go and get something from the cache, which is always going to be there, plus the miss ratio, how many misses we actually have, times the miss penalty. And since the miss penalty is probably going to be something very, very big, we want to minimize this miss ratio as far as possible. And so our cache hierarchy, its main function is to go and reduce this, to make the miss ratio as low as possible, getting it to, parts of a percent or even less, because the miss penalty really is going to be high. On the other hand, we also want to make sure that hit time stays low, because that's a constant factor in our AMAT. So we said that we need to go to provide an ID to tag each unit of data. And what are those IDs? Well, I mean, this may be clear to everybody, but I don't know how trivial it is. Those IDs can just use the address because every single byte has an address. So we can just use the address to ID or to tag those that data. So if we have a RISC-V 32-bit machine, our address is going to be 32 bits long, and we want to be able to address each byte. And therefore, we need 32 bits to tag a byte because each byte has a different 32-bit address. Okay, so for example, let's say we have a cache that's 1 kilobyte or 2 to the 10 bytes of data. Okay, that means we need 1 kilobyte to store the data, but we need 32 bits for each of those 1 kilo entries. So we need 32 kilobytes to store the tags. And that kind of seems a bit ridiculous. So in this case, we have our DRAM over here, which is very, very big, and we're caching 1 kilobyte of data, but we need 32 times that size just to store the IDs. The other thing is that in order to go and look for that, we need 32-bit comparators over here, and we need one for each of the bytes in here. So when we bring in an address, we check versus each of the tags that we have, each of the addresses that we have stored inside the cache to see if it's there. So if we have 1 kilobyte of data, we have 1,024 tags. We need 1,024 32-bit comparators. That is really, really a bit costly. So the question is if we can do better, and of course we can. That's just the kind of general, very, very generic perception of this type of thing. So instead, we are going to store chunks of data together. Instead of storing each byte, we're going to bring several bytes in, starting at a given address. We call a chunk of data like that a cache block or a cache line. And I'm purposely going to interchangeably use cache block and cache line throughout this lecture because both of these terms are commonly used, and I want you to get used to the fact that a block and a line is the same thing. So let's revisit our example. We want to cache 1 kilobyte of data. That's 2 to the 10 bytes. And we're going to choose a cache block or a cache line that is 64 bytes long, 2 to the 6 bytes. So each of these cache lines now, instead of having just 1 byte in them, it's going to have 64 bytes of data that's going to be copied over from the DRAM. And we can see something like this, that if we take it, we have 2 to the 10 bytes total, but each cache line is 64 bytes, so that leaves us 2 to the 4, or 16 cache lines in total in our SRAM. So instead of having 1,024 cache lines for each byte as we had before, now we only have 16, but they're much larger. Okay, so in this case, we can see that if we keep our data aligned, in other words, they all start at this boundary of 64 bytes, what we bring into the cache, then actually 26 bits in the address of all of these bytes are shared. So if we look at this, and this is in hexa, we see that for these 64 bytes, they all start with 00000, and these ones with 00004, and these ones with 0008, and so forth. So we can really share all of these bytes and use that as the tag to identify the line. So we can go and look at all of these, all of the data that's stored in here with one single tag, which is not the whole 32-bit address of the byte, but only 26 bits in that case, because we have 6 bits is what's going to be looking at each byte in the line. So the extra 6 bits that we have here, if we take the whole address, we'll take these 26 first bits, and that is going to be the identification of this entire cache line of all of the data that's stored at this from this address to this address in the DRAM. And then if we want a certain byte in here, we're going to use the last 6 bits to say which one it is, to offset from the first until the 64th byte that's inside here. So this is just an example that I gave here, that we have a 32-bit address and that we're using 64-byte cache lines, and therefore we have tags that are 26 bytes long. But I'm going to continue using these kind of numbers because, as we'll see, 64 bytes is really a common size for cache lines. So let's first look at fully associative cache lookup. And so when accessing the memory, as we said in the beginning in our generic look at the cache, we have to check if the requested address is in the cache. And therefore, we need to compare the tag of the address, those 26 bits that we took, with all of the tags that are stored in the cache. And when we actually compare to all of the tags stored in the cache, to every one of the cache lines, this is known as fully associative cache lookup, because any cache line can be stored anywhere in the cache. The problem with that is that fully associative caches are very, very, very expensive, sometimes to the point where they're impractical. Our first implementation would be to use a comparator. And again, this is going to be a 26-bit comparator, and it's going to have to be on each cache line. So we have many, many, many of these cache lines, and each one of them is going to have to go into a 32, is going to have a tag that goes into a 32-bit comparator, which is going to be compared with the tag of the address that we drive in. And that's going to be really, really, really expensive in order to see that we have a hit and actually pull out the cache line that really did hit in the cache. There is a circuit optimization to do this. It's called a content addressable memory, and I'm not going to go into that in this course, but this is a circuit, a kind of an SRAM type of a thing that we bring a search tag, which would be, this 26 bits, and it will in parallel compare all of these. But this is also considered a very expensive piece of hardware, and they are not that commonly found, even though they are used in different places. So the question is, can we reduce the hardware cost over this type of a fully associative cache? Because if we want to use fully associative cache, it's either going to be very, very, very expensive, or we're going to have really small caches. And the answer to that is what we call a set-associative cache. So let's see if we can just reduce the level of associativity. Instead of having a fully associative cache, let's have a partially associative cache. So let's divide the cache, for example, in two sets. We'll take half of the cache lines and put them in one set, and half of the cache lines in the other set. That means that we take a certain cache line, and due to its address, due to its tag, it can only fit into one of those sets, and therefore we only need half the number of comparators, because it can only be in half of the number of places that it could have been in when we just addressed the whole cache as one. So let's take our previous example. We had 1 kilobyte of cache, 64-byte cache lines, and therefore we had 16 cache lines. But we're going to take those 16 lines and divide them into two sets of 8, and therefore we need 8 comparators. And then we're going to each cache line is either going to be stored in the first set or the second set, and depending on which set the address adheres to, we only need to take all of the 8 lines in that set and compare them with the tag. And this is called 8-way set associative, because we have 8 places that we can put the cache line in instead of the fully 16 places that it could be put in. So this is called 8-way set associative, and if it was a different number of ways or a different number of places we could put it in, we would call it 2 set, 4 set. In other words, N-way, 2-way, 4-way. In other words, it would be called N-way set associative in general. So how do we know which set our cache line is in? Well, bit 6 of the address is actually going to tell us, it's going to be either a 0 for half of the bytes that fit this tag, or it's going to be 1 for the other half. So we'll put the ones that start with 0 in the first set, and we'll put the ones that start with 1 in the second set, and use this index bit to select the set. So this is the index bit. So now our address is divided into the tag, into the index, and into the offset. And if we want to have more sets, we're going to just add more index bits. So let's look at that kind of more illustratively. So how do we do a set-associative cache lookup? Let's have a cache that has L lines, and we'll divide it into S sets. So we're going to take all these L lines, we're going to divide it into S different sets, different places where which each line could sit, and therefore we have to have log 2 of S index bits in order to select the given set that we want out of all those S sets. Okay, so each of these sets now, it includes L divided by S lines. And that means that we can store our particular address in any one of those L over S lines. So we're going to call that N. And the reason is because this is in general called N-way set associative. And this N is called a way. So each line can be stored in N different places or in N ways. The index bit is going to be used to select the set. So we have this, it's going to be log 2 of S of the number of sets, and that means we can use an address decoder to kind of select it. So what we're going to do is we're going to visualize this as our sets are the rows of our cache. So we see that we took our cache and put it into these types of arrays that have tag and data, but the row is going to be selected by the index bit that goes into a decoder. And so you see all of the cache lines that fit in set number 0 are going to go in this first line, and when our index bits are 0, 0, we're going to select this set. And if it's 0, 1, we're going to select the second set. So really, it's kind of confusing, and it may be counterintuitive to what I showed before, but when you want to think about this and remember it, because it becomes very, very hard to remember, you have to draw this on a piece of paper every time you think about it. It's really worthwhile thinking about the sets as being in the rows, because the index bit, it goes into a row decoder that selects one of them. And therefore, the ways are going to be in the columns. So in set 0, we are going to select set 0, and our cache line can be in any one of these 3 places. And therefore, we have to take the tag from each of these three places and compare it with our tag. Okay, so we're going to take the tag and drive it into each of these 3 comparators, and assuming only one of them will hit, we're going to construct a global hit signal, and we're going to also therefore be able to take the data that comes out of that same line that we in parallel pull out and drive it to the CPU. There is another, if we get a miss, we have to take the data from the DRAM, so that's what this mux is talking about. So in this example, what we see here, we have a 3-way set-associative cache. So again, remember, each piece of data, each address that adheres to set number 0, it can be here, here, or here. So that's in 3 different ways. Okay. In general, if we look over here, we have 12 cache lines. We have 4 by 3, right? So 12 cache lines. The number of rows is the number of sets. So there are 4 rows. So S over here equals 4. And the ways are basically 12 divided by 4, 3 ways. So 1, 2, 3 rows, or the number of columns. So that is a 3-way set-associative cache, and we can make different types of set-associative caches. What is the maximum number of sets we can have? Well, obviously, the maximum number of sets is when we only have 1 cache line. Otherwise, we can't go to subatomic type of a level there. And in this case, the given cache line can only be stored in one place. There's only one way left because there's only 1 cache line in a given set. And therefore, it is a 1-way set-associative cache. And this is a very special implementation that needs only 1 comparator. And so we give it a particular name, and this is called a direct map cache, because every single cache line is directly mapped to one from the DRAM to one part of the cache. So let's go back to our example. We have our 1 kilobyte cache with 64 byte lines, and therefore we have a total of 16 cache lines. What a direct mapped cache will have, it will have 16 sets. So there are going to be 16 rows, as you see. And because we have 16 sets, we have log 2 of that, or 4 index bits. So the index bits here are going to be bit number 6 to number 9. Okay, the index bits, again, are going to be driven to a decoder, and the decoder is going to be a 4 to 16 decoder, so it's going to choose one of these cache lines, and it's going to read out, therefore, the tag and the data. And the tag and the data are going to go into this single comparator that we have. It's going to give a hit signal, and the hit signal is therefore going to tell us that the data is relevant. The offset is going to go and select the particular byte or word from the 64 bytes that we have here, and that's what it's going to provide to the CPU. So as a kind of a summary, let's look at an example of an 8-block cache, and let's see what alternatives we have. So what we saw over here is that the last thing was a direct map cache. In a direct map cache, we have 1 cache line in each of the sets. So if we have 8 blocks, we have 1 set per block, or 1 block per set. So we have 8 sets, and that means we only have 1 way. In other words, each cache line can only be stored in 1 position, in one block. And we also only need 1 comparator, and we have 3 index bits, which will help us choose which set we are in. We can have 2-way set-associative. In this case, we take our 8 blocks and we divide them into 4 sets. And that means we have 4 different sets over here, set 0 to set 3, which are chosen through 2 index bits. And then we need 2 comparators, because each of these, a certain cache line can be in 2 positions. So if we look at something that's in set 1, it can be either in cache line 2 or 3. The next step is, of course, 4-way set-associative, which needs only 1 index bit. We have 2 sets, and then each of the 2 sets has 4 ways that we can store a certain address in. And so we need 4 comparators to figure that out. And finally, we have fully associative, where we don't have any index bits in our address, and we can store our address in any one of these 8 blocks. So as a summary, I just want to, again, reiterate over this because it gets confusing, and I know we've seen it many times in the last few minutes, but what is the terminology of cache addressing? Okay, we divide our address into three parts. We have, at first, the LSBs are the offset, and they choose the byte within the cache block we have, or the cache line we have. Remember, we store a cluster of bytes inside one cache line, and so we address them with, this offset. Then we have the set index, and the set index is log2 of the number of sets, and that is used to choose which set our particular address is going to be stored in. And then finally, all of the remaining bits are going to be used for the tag, and so the size of the tag is the address size minus the size of the index minus log2 of the number of bytes in a block.